Okay, I think we are ready to start. So today we have Yotam speaking to us about something continuing Max's presentation from last week, but hopefully without too many assumptions on how well we'll remember.
I will only assume you remember every word, especially those of you who have
Well, every other word, because you can error correct, right? That was the whole point.
Right.
That's what's terrible. Okay, epsilon more than half.
Good. So, right. So this talk, as the last talk, is based on joint work with Max Hopkins here, and also Russell Impagliazzo and Tony Pitasi that are not here. So all the hard questions to Max. Okay. So last time we talked about local list decoding, and Max gave us a very nice introduction about what that actually means. I will remind everybody briefly what this is, but I'm sorry if this will sound a bit unmotivated because I'm counting on something from last week. But basically, right, in error correcting codes, we have this idea where we have some space of messages and we kind of encode it or embed it in a larger space with kind of more leg room, maybe messages over more bits and over, a larger alphabet or something like that. And the task of decoding is a task where, I don't know, you get some word here that may or may not be an actual code word, something that was encoded from the messages, but it's at least assumed to be somewhat close to something that was encoded, maybe some encoding like this. And the task of decoding, or a decoding function, is just a function that takes this W and it's supposed to map you back to the message that was encoded to something close to W. So this is like encoding with noise. And last time we saw that one thing that we can try and optimize for is the decoding radius, namely how much noise can I assume that actually happened between the encoding and the word that I actually receive and I'm supposed to decode. And when this noise was kind of very small, we saw that this task that I just described is indeed possible in many cases, in many error correcting codes. But kind of if I want to assume, I don't know, a lot of noise, like 70% of the word is actually just a random garbage and the rest is maybe correlated with some code word, then kind of I really need to kind of decode all code words that are in a pretty large ball around this W that I'm given. And then I have this problem where there could actually be, another code word in code of F prime in the same ball, and my decoder, it doesn't know to distinguish whether it should give me back F or F prime. And so for this we had this task of list decoding where kind of I'm supposed to give you a list of many decoders, one of which is supposed to decode back, I don't know, one message that's close, the other is supposed to decode back another message, and this was what we called list decoding. And finally, last time we also had this other adjective, which was local decoding, where we asked that these kind of decoders, they're not just existential functions, but they're actually very efficient. They barely look at the message at all. They only query it at Q locations, possibly using some randomness. So I wrote kind of this whole definition of local list decoding, which I admit is kind of cumbersome. So I thought I'd go over it quickly, but to be honest, we won't need this for most of the talk. So kind of if you're not following the order of quantifiers or something like that, kind of don't worry. It's just that it's kind of the main definition and the thing that we're heading towards in this talk. So maybe it's good to remind ourselves. So locally list decodable code, an LLDC, is a code that has three parameters, epsilon, q, and l. And it's just a code which I think about as this encoding function, where in addition, I have some algorithm that can spit out like decoders. So not one decoder, but a list of decoders. How many? This L over here. And every decoder, it gets as input a single bit on which it is supposed to it's supposed to answer kind of what's the ith bit of the message that it's decoding. And it also gets query access to some word W, which we hope is at least somewhat correlated with code word, but it can only access it on Q locations, Q this second parameter here. And finally, the guarantee that we want from these from these localist decoders is that if I have a message in like the n-bit string, in like the source, whose encoding is non-trivially close to W, how close? 1 minus epsilon. So we should think about epsilon as at least a small constant, if not something that's even smaller, maybe, asymptotically goes to 0 with some parameters. In any case, whenever I have something that's non-trivially close to the word that the decoder gets, then at least one of my decoders should decode back my function, namely, it should give me back f of I for any index I that I put. Last time we saw that this is kind of too optimistic. We can't actually have this happen deterministically all the time. So we instead add some probability here and ask that the probability be higher than some constant, maybe 0.9 for this talk. But I kind of want to stress that the probability here is only on the queries and the internal randomness of the decoder. It's not on this I. And finally, I see Avi's here on the Zoom. So I will use another color. No, it will only be for very little use. We also had a relaxation of this definition, which we called approximately locally list decodable code. So I'll add another A here in red, where the only difference in this definition is that instead of asking that this holds on all I, I'm allowing the decoder to kind of give up on a few indices as long as it's not too much. So I should write here for all I except some small set of, say, 1%. Okay, so for 1% of the I's, I might answer different than F all the time. I might answer just randomly, I don't know. But except for some like small bad set of indices, I am basically supposed to decode back to F.
So this is sometimes called relaxed, so?
So relaxed locally decodable code is a different notion.
This is you're allowed to reject.
You're allowed to reject, but if you're not noisy, then you always have to give the right. It's different. I know there are some kind of equivalences, but I don't think they work in like the list decoding regime. So this is actually the.
So one weird thing about like approximate locally decodable codes is the block length can be smaller than the message length.
What can we?
The length of your code can be smaller than the message length because you don't have to recover all the bits. For example, if I was giving you like as many queries as you wanted.
I see. So that's like this is a weaker notion.
Right.
And your normalization is the two random words at distance 1 from each other?
Yeah. Like this is the normalized Hamming distance. So it's like 1 over the number of coordinates times the number of coordinates on which these two differ.
So for randoms, should be 1/2, right?
So it depends on the alphabet, right? Like here, you see, actually we'll have quite a large alphabet here. This is like also a parameter. So I really actually think about 2 random words as being of distance 1. But of course, this is super interesting for binary alphabet in which case you're, of course, right.
And also, how do we think about these decoders? These are like circuits? Or...
Yeah, so you should think about them as circuits. You can also think about them as algorithms or, there's also a lot going on in like what it means efficiency besides number of queries, which I'm kind of sweeping under the rug because it's already, look at this definition, it's long. But yes, you should think about them as circuits and of course you should also care about their size, their depth, like various notions of computation
circuits with Oracle access to this.
Sure. Once they're circuits, they have to have Oracle access.
You get the same definition if you, instead of 1% of I, you said at most 1% of W or at most 1% of F. Like, I guess to me, it seems somewhat arbitrary that you said like for most I instead of for most W for all I.
Oh, so it's not.
Like, I understand the order of quantifiers, but it seems like you chose that somewhat arbitrarily.
Oh, so this is not chosen arbitrarily. Maybe like last week we saw that this definition works very well with composition, and it also has somewhat other applications. The picture that maybe I want you to kind of get in here, like suppose this is W and this is like the encoding of F, or F prime in this case, and like here is actually F prime. My decoder, it might not, point me directly to F prime, but it's like pointing to something that's like very, very close to F prime.
I see.
I'm not decoding exactly to F prime, but to something that's very, very close.
Okay.
So this is like, I'm almost recovering the whole message in this probabilistic sense.
It's maybe also worth noting that in terms of like getting 99% of the F or something like this, if I could do that, usually the codes we have, there aren't combinatorially that many F, so I could just run it like a few more times and then it will cover everything.
I see. Okay.
That's not much.
Cool.
Okay, great. So last time we talked about a specific class of code, which we call these direct product codes. And I will maybe actually before that, maybe let me say where I'm going with this. So Max last time talked about some construction, which we call kind of the baby version. And today I want to actually prove, I want to construct a stronger version of the Max's construction. But most of what we'll do at first is just kind of remind everybody what happened in the last hour of the last talk. And then we will kind of take a deeper dive into why the construction that Max described works as it is. And after that, we will kind of abstract out some properties in this construction that we will try to kind of use towards constructing a different and better code in terms of rate and so on. So really, I'm kind of recapping here, and sorry for those of you who actually remember like most of the last half hour what happened. But for those who don't, this is like a slightly less dense version. So the codes that we talked about last time, they weren't just arbitrary codes, they were a very specific class of codes. So these codes are called direct product codes, and in these codes we had some bipartite graph, whose two parts I call V and S. And let's assume that VS is also biregular. In all of our examples it will be, and it simplifies things. So I don't know, let's suppose the degree of a little v down here is R, and the degree of little s up here is L. In these codes, we encode strings that are indexed by the points of v, so I should also think about them as functions from v to 0, 1. And my encoding encodes to functions indexed by s, and they have L bits of output. And we saw last time that when I encode a function f down here, at the point s, we just record the values of f on all the neighbors of s. So we wrote this last time as f at s is just equal to the function f restricted to s, actually the neighborhood of s, but let me not add more notation. Right, so of course, the regularity of the s's here, right, this is like log alphabet size or alphabet length. I also claim that the rate of this code is just 1 over the degree of every vertex here. One way to see this is to actually kind of calculate the number of bits you need to write the function here, or the number of bits you need to write the function here. Another way is to just see that if I have here r edges, it means that I'm duplicating the bit over here exactly r times. So we get a blow up of r, or a rate of 1 minus r. So of course, in terms of error correction, right, we often like codes that minimize a rate and alphabet size. So we usually want both L and R to be as small as possible. I will tell you the specific construction of a direct product code we talked about in a minute, but before that, I also kind of want to tell you about the actual computational task that we will try and solve in this talk, which is not local list decoding, but it's actually local list recovery. So we kind of mentioned this in the end of last time. Let's kind of interpret what local list decoding actually means on direct product codes. Right, in direct product codes, I will use white here, we're getting some noisy code word, right? So we're getting like some W here, and I can interpret this W as kind of giving me one function per set or point here above, whose domain is like the neighborhood of the set, and it goes to 0, 1. And when I'm decoding, right, I'm assuming the function is like non-trivially close to my W, which means in this case that there exists a set here which, you know, has some non-trivial size greater or equal than this parameter epsilon, where on the points here in W, the functions that I get for this point is equal to this f restricted to s. And using this fact, one of my decoders is supposed to decode this like function f on all or most of the points. A related task that we talked about last time, which is kind of both easier and harder in this sense, is the task of list recovery. In list recovery, we get a bunch of lists, one for every point, where in every list we don't have one function on the domain of S, but we have G1, G2, we have many functions on S. So in general, this is kind of like many alphabet symbols, but here let's kind of think about functions. And in list decoding, what I want is to decode functions F that appear in all the lists. Decode functions F that are, of course, from the message space, such that F appears in all the lists. So why did I say it's easier and harder at the same time? On the one hand, in local decoding, I'm like only getting one function per point here, and here I'm getting a whole bunch of them. On the other hand, in list decoding, I really only want to decode functions that appear in all the lists. So in all of these points instead of just like a small set. And last time, let's remind you, we saw some reduction by Guruswamy and Indig from 2002 that showed that if I know how to solve this list recovery task, then I actually know how to construct list decoders. So list recovery implies list decoding. So kind of let me just modify the definition here so that kind of we have the formal definition of list recovery, and then we can actually continue and construct codes on which we can solve this list recovery task. But maybe before this formal definition, does anybody have questions or comments?
Explain to us this last slide, what it means.
This thing, right, so we talked about this last time. It turns out that if I have a code on which I can solve like this list recovery problem where I get lists and I need to decode functions that appear in this list, then you can kind of transform this code into a code where you have basically the same rate, query complexity, and so on, that will solve this task.
So, but it's on a new code.
Right, so it's a new-ish code, right?
Yeah.
What you kind of do, you like take all these points and you kind of bunch certain points together using some kind of expander. This is It's not a theorem in their paper, it's probably a lemma by Swami Indik. Nowadays, I think it's considered standard, but like, I think it's very insightful. So it's not immediate, you're not supposed to see why this works. Right, so.
To give us a definition of list recoveries.
Right, so I'm just going to change the definition here, because really we're only going to use this. So, right, so here, let me change the epsilon to I, and change the D here to R, so locally least recoverable code, or approximate locally least recoverable code. Same code, still get a bunch of decoders. Now every decoder doesn't get query access to W, but it gets query access to these lists, okay, where this I parameter here governs the cardinality of the lists. Okay, so we have at most one function per list. And now,
At most I functions.
sorry, at most I functions. Thank you, Irit. I woke up at 3 a.m. No, seriously, so I'm tired and I might say things like that by mistake, so correct me. Anyway, right. And now, the things that I want to decode are not functions that are, I don't know, 1 minus epsilon close to a list, whatever that means. Now, I want that for any message, such that for all the S's, F restricted to S is one of the functions in the list. I want to decode it as before. Okay? So without the red, this is locally least recoverable code. With the red A, I also allow myself to give up on a small set of indices. These are analogous.
How big should I think of I as being?
Right, so in this reduction, I should look like 1 over epsilon. So kind of the bigger I is, then the harder the task becomes. But I mean, think even of I equal to, this is already maybe like a non-trivial task, right? Like you have some function f that appears in all the lists. Now, I mean, but you don't know which function in which list corresponds to f. So kind of you're already trying to kind of match up functions and it's not. So I mean, in applications, I should be quite large, but I like to think about I as like 2 or 3, and already it kind of conveys the kind of the problematic aspects in this problem. Okay. Good. So let me remind you what was this baby version construction that we talked about last time. So last time we did this direct product code that let me call it the baby code. Right. So B, the points.
You should call it 3 a.m.
Maybe I was awake from by my own. Maybe it's not related to a certain baby.
Yeah, I've heard she sleeps in the night.
No, she actually, I mean, she woke up every 10 minutes, but she went back to sleep. And only I eventually couldn't fall back to sleep. But Gil did a wonderful job falling back to sleep. Never mind, I'm recorded. Okay, so here's my baby code. We have some ambient vector space, FP to some even dimension 2D. So what are my points on one side? They will just be D minus 1 dimensional linear subspaces. What will be points on the other side? D plus 1 dimensional linear subspaces. Okay, so like almost middle dimension. And I will connect little v to little s if V as a subspace sits inside S as a subspace. So this is kind of the code. Kind of the P that we need to take, the field size here. This is, you know, any prime power. It should be some polynomial in the list size and also log v. So this is kind of what you should think, but I ignore this. Think just as like a large enough P. I'm just writing it for myself. Good. And this was basically the code that we kind of tried to describe some kind of list recovery for it. Maybe before that, let me kind of just give you back the calculation of the rate and the alphabet length, just so that we will see what we're improving. So this graph is not just biregular, it's actually regular. In fact, it's isomorphic to itself when you flip it, like to take S to be V and vice versa. And like L, which is equal to R, okay, I mean, it's roughly something like P to the 2D. And if you take P to look like this will sort of look like some 2 to the square root log n, log I, or something like that.
Why do you say 2D and not 2?
These are D minus 1 dimensional subspaces. You should think about like every D plus one thing in the neighborhood as like, right, okay. Good. In any case, this is just kind of the calculation, just so that you will see that the rate is, of course, inverse this, and the alphabet length is inverse that, and kind of our real goal is to reach today a rate that looks like some poly epsilon divided by log n, and not 2 to the minus this, sorry, epsilon poly 1 over I times log n, something like that, and not some kind of pseudo like quasi-polynomial here. But this we will only get to in the end of the talk. For now,
What is capital N?
right, sorry, I should, right, so I'm doing this, thank you, I'm doing this direct product code, and like I'm thinking about V as having like the n bits of the message space that I'm encoding. So sorry if I'm kind of changing the size of V and n, it should be the same.
So n is the size of it.
Right, sure.
Why the no?
I think is on the numerator, right? Like I is a natural number.
I is a natural number, that is true.
Okay, no, sorry.
Rate is
Rate goes
inverse.
down with
Like
I.
as I grows larger, this is a harder task. We will need more redundancy, and the rate grows.
Okay, perfect. Yeah, I was confused.
Great, great. We all are. Good. So this is just like some parameter counting in the code. It's not very.
This is your goal, this rate? What is the rate of the baby code?
Right.
That's the goal or that's the rate?
The rate of the baby code is like 1 over R, right? So the rate of the baby code is 2 to the inverse, whatever's written here, right? What we want to get to in the end of the talk is rate that doesn't behave like this. It's just a polynomial in I and log v, not this 2 to the square root log. Okay, to do that, we will need to do some more work. But kind of before we do that, let's see why this code works, and let's see its decoding algorithm, which later on we will use the same decoding algorithm for a different set system. So when I do list recovery, I actually need to tell you, first of all, how do I kind of determine the decoders? What this like algorithm that splits up the decoder does? And second, what every decoder does. So my algorithm will just randomly sample some kind of starting set, little s inside capital S, uniformly at random, and it will spit out decoders. Decoder 1, decoder, let's call it SG1, decoder SG2, and so on, up to decoder SGI, where all these G's are in the list of the starting point S. Okay, and this is up until now, I haven't said anything, right? I'm just saying what the parameters of the algorithm is passing to some kind of decoding circuit. And again, last time we saw that these decoding circuits will start with this like starting point S, and they will operate under the assumption that the function that they got here, this one of the functions in the list, is actually part of the global function that we are trying to encode. Of course, one of them will actually get lucky, and this will be true for one of them. And the way they will work is that they will try to kind of propagate this information to other lists. So for example, suppose we got some decoder that actually got F restricted to that starting point. The way this decoder will propagate this information, and I will give the exact algorithm in a second, is the following. If it so happens that this set S actually intersects with this set S prime, here this decoder says, okay, I have here like
S is a, what do you mean by set S?
Right, sorry. So, right. So I think about these things as kind of, I identify them with their neighborhood. This is why I'm saying a set S. And so when I say S intersects with S prime, I mean that their neighborhoods have some intersection over here. Thanks. Good. So the way this decoder will operate, it will have the function f that's defined only on the points of S here. And on S prime, I have a list, maybe it contains G1, G2, and so on, of LS prime. And it wants to kind of distinguish which of these G's in LS prime, or which one of these G's is actually equal to this F. And the way it will do it is just by saying, take the G such that GI is equal to this F restricted to S intersect S prime. So the way we're going to identify which function is the right function here is just a function that agrees on the intersection with the function that I get here as a parameter. This is going to be kind of our heuristic. Of course, we saw two problems. Let me just finish my sentence. Okay. One problem with this heuristic is that, I don't know, it could be that G1 happens to agree with the function that the decoder has on the intersection, but it actually disagrees with the function we're trying to decode on all the rest of the set. This can happen. We will claim that it happens only very rarely in this subspace construction, but it will require a bit of work. The second problem that we talked about last time is that, this decoder is getting as input some set V, and it could be that any set that actually contains V is not intersecting S. And so we can't just say, let's look at their intersection, because there may be no intersection. And last time, the way we solved this is we saw that these decoders should actually kind of find a path of sets where each one intersects the other, and then we will use this like heuristic one time after the other up until we kind of decode, we kind of find a good candidate for what F should be in the list of a set that contains V. So now I want to write what this decoder does formally, but maybe first,
So maybe I'm missing something. So what is the elements of the list? Like those guys, you construct them or you have them in
Right. So right now we're thinking about these elements of the lists as functions whose domains are the neighborhoods of these sets over here. Right?
Yeah, but that's what you want to construct, or that?
No, so this is something that we're given query access to.
But is
Like
it
the
constructed by an
inputs.
average?
Right, this is
That's the
the
received
right.
word.
This is like the received word. Only it's not the word. It's like list arbitrary.
It is adverse. Yeah, it could be constructed by an adverse. Okay.
So I think the bipartite graph is not the way you're thinking about it. So really you have V, a set of vertices, and then you have S, a collection of sets of those vertices. And for every element in S, every subset like that, you get a little list of these. That's your input.
Sure.
And your goal is to find one G per set that kind of is your message.
Sure.
Find code.
Like under the condition that there exists a global F that matches everything.
Right.
Okay.
Right. It's not unique. So this can happen, right? It could be that two G's here, and somehow when I write the algorithm, we'll need to deal with that. Like,
I guess why should it be okay for all of the G's to have the same intersection on S?
I mean, look, you
Why
can
does
have
it-
all the G's that are like very similar to one another, but I mean, that's not so bad, right? Because at least in the approximate version, we're all right and like erring on like a small set of things. So if I don't get, if I don't get exactly F here, but something close, on most of these vertices, I'll answer probably the correct answer, and on some I will err, but this will be like part of my error set. So, but it's a good observation. It could be that I have many possibilities here, and I really kind of have to take that into account. Good. So here's here's what the decoder actually does. Allow me to slightly abuse notation and assume that my decoder actually got the correct function, of course, on S, okay? And so here's what it does. First of all, okay, I mean, what are we supposed to do, right? We're supposed to decode a vertex. So this, of course, gets as input some vertex here. So at step 0, it samples a set which I will call ST uniformly at random among all the sets that contain the vertex. Okay. In other words, I'm sampling some element S here whose functions in the list have some opinion on P, whether it should be 0 or 1. And what we're going to try to do is to identify which functions here in the list of ST are close to the global function we're trying to decode. In the first step, we will find a path of intersecting sets. Let's start with S0, which is the S that we got here. S1, S2, up to ST, so that every pair of sets here intersects significantly. In particular, what I'm going to require that as D+1 subspaces, the dimension of SI intersect SI plus 1 will always be D. So in particular, if two D+1 subspaces have an intersection which is a D-dimensional subspace, they contain many D-1 subspaces together. And how am I going to do this? We kind of talked about this last time, right? I'm just going to sample some basis to S0, some basis to ST, and then I'm like changing one vector after another. There are some details here, but this is really basically the way we route here. So let me just kind of write here basis X change. In the second step, I'm going to iteratively identify in the lists of S1, 2, and so on functions that should be close to the global function we're trying to compute. So let me set T0 just to be this function inside the list of S0. And then we will compute sets Ti using Ti minus 1. So the sets Ti contain all elements in LSI such that there is an element in the I-1 list where G prime agrees with G on all the neighborhoods of Si and Si minus 1. Okay, so starting from one function here, we take all the functions in the list that have the same values on all this intersection. After that, we look at all the functions in the list of this that have the same values in the intersection of one of these functions, and so on and so forth. after that, we will randomly sample G in the final list of ST and output whatever that function says on V. Okay, and hopefully this thing is supposed to be close enough to F, even if it's not identical to F.
Yeah, but that's what you do for number one. You just take for the basis exchange. Yeah, do you choose it?
Right, so I will choose it at random. Like, right, I can write S as like some span of x1 up to xd plus 1. I can write ST as like some span of y1 up to y d plus 1.
Yeah.
And then like, in S1, I will replace this x by y1. In S2, I will replace this thing by y2.
Oh, so the randomness is only the basis that you choose at the beginning.
Yeah, the order of...
okay,
right.
basis with order of basis.
Right, and, if you kind of really push me, right, you can say, oh, but what happens if what I get here is not a d plus 1 dimensional subspace, so I kind of really need to take bases here that also take into account the intersections. There's messy details here, but this is what you should think about.
Why do you need random?
Oh, that's a good question. I will address that. Okay.
And also in the final TT, there are like one over like I to the T many possibilities, is it?
So look, in T sub I, we're only taking elements in the list of Si. So T sub T are only elements in the list of St.
Oh.
There could be I elements in total, right? Like this could be equal to LST. It could be a partial set. Okay, one thing that maybe is good to observe is that if indeed F is in all the lists, right, then if I start here with indeed the function F that I'm trying to compute, right, in the list of S1, F also appears, so it will also be in T1. In the T2, it will also be in T2, and kind of inductively, it will appear everywhere. But there could be additional functions here. What we will argue is that typically all functions that are here, even if they're not equal to F, they're very close to F on ST. Good. Great. So this is the decoder. Where am I in terms of time? Good. Awesome. And maybe the next thing I want to do is kind of remind you why this thing works. So the actual theorem that I need to prove, right, is that this baby code, if P is the value that I set here, baby code is I Q L, which is actually also equal to I, approximately locally least recoverable, where Q is again some polynomial in log n over epsilon, and the rate is like is sub-polynomial and so on, but this is kind of what we're heading towards. I'm not going to prove this theorem in full. What I do want is to kind of prove some kind of main lemma.
Yes, there's no epsilon here.
No, sorry, I always do this, right? Thank you, Max. Right. What I do want to do is to prove some kind of lemma, which using this lemma you can prove the theorem. And the lemma is basically this. Ignore the fact that I'm getting an input here. Just think about both this parameterized set S and this ST as sampled uniformly at random. I want to claim that in this case, if I sample S and ST uniformly at random and independently, when I do these steps 1 and 2, I will get lists where all the functions are actually very close to F. So, I'm going to write this in, like, I'm not going to write all the details, but let me write it like this. The probability upon sampling independently and uniformly S0 and ST, where I take the decoder with S0 and F, and I use it on ST, so it will output, I mean, it doesn't output this, but it does this in like step 1 and 2, this final list. I want the probability that every function in T is actually very close to F. So I want this to happen with very high probability. To go from this lemma to the actual theorem, it's just a bunch of Markov inequalities that I kind of don't want to do. This is the main step, saying that if I sample two of these independently and uniformly at random, if I have F identified in S0, I will only identify functions here that are very close to S with very high probability. And we actually talked about this last time. Maybe I'll leave this up. But say again, sorry.
Like, are you saying this is independent of little t, no matter how many steps I take?
Yeah, so you always take your at most d plus 1 steps. But among all these t's, it doesn't matter if you like you could just take, I don't know, 2 steps sometime, and you can also like take, I don't know, d plus 1 steps actually most of the time. But still, like, this probability would be high.
So we're still in the baby code.
Yes, yes. But the reason I'm proving this lemma here is that this lemma, the proof of this lemma will also work for any code with certain properties. And like most of this proof of the lemma will unfortunately just be kind of defining some kind of invariants that come from these graphs and their properties, and then seeing how these invariants kind of imply the lemma almost immediately. So this is what I kind of want to do now. So I want to actually give you a sketch of the proof of this lemma, and it will kind of highlight what properties we're looking for in these systems of like V's and S's. So here's player 1 in the proof of the lemma, the decoding graph. I will call it G. So the decoding graph is basically just a graph we're walking on when we're finding this routing from S0 to ST. So the vertices in the decoding graph are just S, and we connect S to S prime if the dimension of the intersection is D. And of course, when I said we find the path of intersecting sets, I really mean that we actually have a routing scheme here, right? We have some function where I give it S0 and ST, and it outputs some path, which I'm using as a subroutine up above there. And what are the properties that I need from this routing scheme? First of all, I need the fact that it's short. Like if I call this P is always at most D plus 1. Why is that? Because I'm doing this basis exchange, right? And I'm doing D plus 1 steps here.
It was your field side.
Oh, sorry. P is maybe a bad letter for a path. Maybe R. Is that okay? And the second property that I need is that this routing scheme is kind of random enough so that no edge in this graph is used too much. So formally, this has a name. This is called sometimes unit congestion or low congestion. So I will just say a routing scheme or a routing algorithm like this is called unit congestion. if the edges that I get in this routing scheme are basically just distributed uniformly at random. So formally, I'll give like the formal definition in a second, but before that, maybe kind of let me give you the picture of what I want and why. Formally, right, we're like looking at this distribution where I sample endpoints here, and then I look at some routing that I'm doing over there. So, you know, I get some S0 and I do some routing ST here. Inside this graph, right, we're trying to like identify these T's. And in some of these edges, it could be that maybe I agree with, you know, F in the intersection entirely, but outside the intersection, I kind of disagree. These are kind of bad edges. I don't want to land on these bad edges very much. Okay, there's like a couple of bad edges here in the graph, and I don't want to land on these bad edges very much. We will argue that there are very few bad edges, but if I don't say something about the routing here, then a priori, you might expect that this routing kind of always goes through a bad edge. And remember these lists, I mean, somebody is giving me them, they can be adversarial. So I don't know anything except for me arguing in a minute that there are very few bad edges. So having unit congestion routing is kind of my solution of saying no edge is really used all that much. And so if there's a small set of bad edges, most of the time I will actually miss. So formally, what? Yeah. So low congestion kind of means that you won't like use this edge all that much. So like there's not much congestion in that. And this is like congestion 1. So this is like the terminology. In any case, this is unit conjunction if the following distribution
is the lowest possible.
Right.
You see congestion if edges used 3 times more than
Why that? Use that.
Okay, so a graph is unit congestion if the following distribution is actually just a uniform distribution on edges. And what is the distribution? Let's call it D. First of all, we sample 2 endpoints independently and uniformly at random from my graph. In this case, it's like the decoding graph. 2, I route, let's call it R. I do my algorithm to route. And 3, I randomly sample an edge from the resulting path that I get uniformly at random. Right, so this is a distribution. I look at the path I sample that I get from my routing from random endpoints, and I look at like a random edge over there. This is a measure of like how of like being, you know, very kind of very random, and you can extend this. Like instead of unit congestion, you can talk about other notions. Maybe I don't want this to be exactly like the uniform distribution. Maybe I want it to be I don't know, like just statistically close, or to have high enough entropy, or some like missing small sets. You can work with a lot of these definitions. Somehow, I found that this is the cleanest one to do in this talk. Good. So this is player 1, and
It's a very strong notion, right?
right, but we have it, and I will claim without proving that the routing in step 1 is right UC, like this capital, so unit congestion. And why is this? I mean, you can imagine that like no edge is really preferred here if you're just like picking random bases and exchanging them. So let's not do this. Good. What's player 2 in my proof? It will be what we call the local graphs. So we also mentioned this last time, but I want to kind of define them. So for every little s inside big S, we have what I would call the local graph. which I will denote by G sub S. Okay, and remember from last time, this graph was this graph that kind of allowed me to argue about the intersections of this specific S here that I'm taking. So this was a bipartite graph. On one side, we actually had the subspaces inside S, these D-1 subspaces. On the other side, we actually had all S prime that intersected this specific S, such that and we connected every S prime here to V if V appears in this, inside this intersection. Right, so the reason
is all the V's that are contained in S.
Right,
So
yes,
these are, S is D+1 dimensional,
right,
these are D-1 dimensional.
Correct.
And the top is all the S primes that intersect X.
right. I also want to give you a picture. Like this is S, and inside it, I think about all the subspaces of S, all like the points that the functions are defined on. And I want a way to argue about the intersections between S and other subsets. So, right, so for every S prime here, right, I have this intersection here, and like, so I can put S prime as somebody in like this upper side of the bipartite graph, and I connect S prime here to all the points that appear in the intersection. And then I will have also some S prime prime, and I will connect it to that, and so on and so forth. And where's the writing? Maybe I want to keep, yeah, I should keep this, right? So up until now, this is just a definition. But the property that I want from this graph is what's called sampling. So what is a sampling property of a graph? In a graph, you can look at subsets of vertices A, and you can kind of associate with them relative sizes. So let's write, for example, PA, right? This is like the left and the right sides. This is just like the relative size of A. But you can also look at the relative size of A with respect to neighborhoods of vertices on the other side. So for example, maybe A, has significant size here, maybe 0.1, but it could be that for some S prime here, its neighborhood doesn't see S at all. Or maybe for some S prime prime here, its neighborhood is like maybe entirely or almost entirely contained inside A. And in general, right, like sometimes, you actually kind of see A in the right proportion here, that's kind of close to this.
You wanted to divide by R or by L?
Sorry. Yes, thank you. So I will also kind of look at this notion of probability A given a vertex on the right-hand side, which is kind of just A intersect the neighborhood of the right-hand side. So in this case, I'll kind of abuse notation and write S intersect S prime over S intersect S prime. And I mean, I can give the formal definition in a second, but basically in sampler graphs, these two quantities are almost identical for most of the R primes.
What is this?
It's a point here. Oh, sorry. Right. I was kind of defining it specifically for this local graph where S is kind of fixed. So, thank you. Okay, but in general, kind of you're just looking at the relative fraction of A intersect the neighborhood over the whole neighborhood. And so don't think too hard about the definition. Like you need to quantify this, but basically in sampler graphs, for almost all points here on the other side, they look like this. The relative fraction of A inside their neighborhood looks like actually the relative fraction of all A inside all this left-hand side. So kind of formally, you say that some graph, or specifically GS, is an alpha sampler if the number of kind of S prime in the right-hand side, where A and A in the neighborhood of S prime differ more than alpha, is at most alpha. I'm kind of using alpha as this small quantity that appears both inside and outside. You can, in general, use more parameters. Again, I really just want you to think about sampler graphs as graphs where for every A in the left-hand side, this and this are most of the time the same quantity. Okay, and for which A's we're going to use this? We're going to use this on A's that look like this, all points inside S where f of v is different from GIV for some GI in the list of S. And I just kind of want to point out now that if we look at sets A that specifically look like this, the relative size of A like this will just be the distance between F and GI.
So Yotam, here do you mean AI should be for a fixed GI?
Right, for this is like for fixed.
It's not like the union.
No, this is not a union. This is for some fixed GI. So if you look at A, this would actually just be the distance between F and GI, right? It's like just the number of vertices normalized that F and GI disagree on. And if you kind of look at A given as prime, right? You kind of chase the definition and you see that this is just the distance of F and GI, but only on the neighborhood of S and S prime, which is the intersection. So the reason that I'm going to use this sampling is that I'm going to argue that because these G's are samplers, most of the time, the distance between F and a member of the list globally on all S is just F from the member of the list locally inside the neighborhood. So, any questions on this before we try and prove the lemma?
Why did you start talking about players?
Right, sorry, I'm using slang, but like objects that will appear in the proof.
Characters.
Characters, thank you.
Is that help? Well, I like characters in the play? In the
Like the main dramatist persona.
Yeah,
okay.
sorry, this probably terminology was maybe non-helpful. I was just talking with Irit today about the fact that sometimes as non-Americans, we kind of translate, like we don't, so you're right, like it's a metaphor. It's not players in some interactive game. It's
just quite a charged term.
Yeah, I agree in retrospect. Thank you.
By the way, if you want to take a break.
Yeah, I think we'll do like 5 minutes of this lemma and then we'll take a break. Okay, so here's the kind of proof sketch of dilemma. Let's see. So let's kind of define a set of bad edges in the graph to be what we kind of said before. So in the decoding graph, G, an edge, S prime, I call it bad if there exists a function in the list of S or in S prime. I will just write the condition for S, but it should be symmetric, such that the distance of the fixed function we're trying to decode from this function on the list and the distance from this of the same two functions, but in the intersection of S and S prime is large. Right.
To clarify, so F is defined everywhere,
Right.
but G is only defined on S.
Right.
So when you say distance
Right,
F
so
and G,
I should
you
write.
get one S.
Right. Thank you. Right. So I want this distance to be large. How large? I need to actually write some parameter here. Don't think about it too much. It's here if you kind of want to follow, but you shouldn't. So anyway, I should just write here large. Okay. And what should I erase? I kind of want. I want this to still appear.
I think
Maybe I will go. Oh.
All the way.
Great. Where was I? Right. So, kind of, here's step one in the proof. The probability just over edges in the graph, the decoding graph, that are sampled uniformly at random, that is bad, is very small. Is also less than, I don't know, something like this. And to prove this, which I'm not going to prove this, but I'll kind of just hand wave. To prove this, you need to argue that the graphs, these local graphs, GSs, are actually sampler graphs. This is true when P is large enough because these graphs, basically, they look like all these like subspace versus subspace graph. I'm not going to do this, but let me kind of just say, when P is large, these are samplers. And so using this interpretation of sets A as like distances, you can show that if an edge is bad, then there is like one set A here where this like S prime inside the local graph of S or vice versa, it kind of violates a sampling property. So I'm not going to prove this, but if you have questions, then like, I hope it's at least believable. Step two in the proof of dilemma is just to say that because the routing is unit congestion, then the probability over S0 and ST that there exists an edge that is bad in the path in routing of S0 and ST that is bad is very small. How small? 0.01, something like that. The whole point here is that because a uniform edge in this path, if I sample these uniformly at random, is itself a uniform at random edge, right? And this is like unit congestion, then the probability that some edge like this is bad is also going to be small, just because the number of bad edges are small.
It's just the union bound.
Just a union bound. There is nothing here. And like the third step is just to say that if there are no bad edges, then the probability in the lemma, or the event we're bounding the probability in the lemma holds. Namely, that all functions in the last list will be close to F. And here, maybe I also just want to hand wave. The proof is just by some kind of induction. Like you start with T0, which, right, it's just F, or again, to be kind of more formal, it's F restricted to the first set in the path. But if you know that on, I don't know, here's SI, all sets, or sorry, all functions G in TI are actually close to F, like inductively you're using this, I will also argue that in Si plus 1, all the G primes in Ti plus 1 are also close to F. And the reason is that if G is close to F on all of Si, then it also means that G, which is in Ti, is close to F also if I restrict it to the intersection. I'll just write like this. And why is that? It's exactly because the edge is not bad. The distance on F on all of this is roughly equal to the distance on F on all of this. But remember what Ti plus 1 means. Ti plus 1 are all functions that agree on the intersection with one of these G's. So for every G prime I have here, right, it actually agrees with one of the G's that was close on the intersection to F. So I can also get from this definition of Ti that G prime here is also close to F on the intersection. And finally, this edge is also not bad with respect to Si plus 1. So this also implies, right, that if I'm close to F on the intersection, then I have to be close to F on like all Si. And so the actual proof, sorry?
Si plus 1.
I plus 1, thank you. The actual proof is like some counting and controlling the error, and we're not going to do it. But these are basically like the 3 steps on which, like, of why this lemma holds. So maybe now is a good time to take a 3-minute break, which will turn into a 5-minute break. And after that, we'll try to digest this proof a little bit and do some other stuff. Okay, so let's continue. Good, so just kind of to digest the proof, what were the key properties that I needed from the set system? Right, property number 1, I had these local graphs, and I need that these local graphs were sufficient samplers. I'm not going to write parameters. What is the second property that I needed? I needed that in the decoding graph, which I called G like this, I had a short routing scheme, and that this routing scheme was also unit congestion. And if in general I have these 2 properties with good enough parameters for whatever it means to be sampling and so on, then I can just do the same proof and get a locally least recoverable code. Of course, here is like property number 3 that I don't need for this proof, but I will want in general to improve my codes. I would like the regularities of these bipartite graphs in VS to be small. So in general, I'd like these 2 regularities that we had to be some poly log V and I. And what we're going to do in like the next 40 minutes is just to prove this proposition where kind of there exist V and S with these 3 properties. Okay, and how are we going to do it? We're going to use high-dimensional expanders. So I don't have a whole lot of time, so I'm not going to kind of define these objects like in full generality. I'm only going to define like 2-dimensional high-dimensional expanders. So here's the definition. A 2-dimensional lambda high-dimensional expander is a 3-partite graph or connected I'll call it X because that's how it's usually called. It is 3 parts, X1, 2, and 3, such that for every point in X, the neighborhood of X, which is sometimes called link, thank you, sometimes called the link, sometimes it's denoted X sub S, is a lambda expander graph. So here, when I'm writing expander graph, I mean a spectral expander graph. Second largest eigenvalue is less than lambda, and I mean there's too much background, so I can't say too much about expanders, but it kind of suffices to know that if I have a lambda expander graph, then the graph will also be a good sampler. And so like for good enough lambda, we'll kind of get these local graphs which are samplers.
How big is this link that you're?
Right, I mean, a priori I didn't say nothing, right? It's just a definition. So really we're just looking at like this nice tripartite graph. And like for every point here, which I'm kind of suggestively calling S, I can look at its neighbors on the two sides, and I can look at like the the vertex-induced subgraph only between these neighbors, and this is supposed to be kind of a small expander graph.
So this isn't a 3-uniform hypergraph. This is genuinely a graph.
So this is just a graph. There is this traditional way of defining a high-dimensional expander, where this X is actually a simplicial complex. These triangles here are just like they're triangles, like as in a hypergraph. I'm not doing this definition mainly because it kind of suggests maybe a different way of encoding using HDXs, which actually works less well. This suffices for our talk, but
I was just confused because you had links and stuff.
Right. So for me, like I said the neighborhood, and I'm kind of just calling it a link so that people that know HDXs, they will know that this is the definition that we're looking at. There is a way to actually think about this as like a hypergraph or a high, something that really has high dimension. Really, kind of for a half an hour definition, this is.
No, I'm happy. Thanks.
This is enough. Let's give a couple of examples. First of all, okay, like example 0, the complete bipartite graph, not bipartite, the tripartite graph. What will be a neighborhood of a point in this tripartite graph? It will be the complete bipartite graph. So if you know something about expanders, this is like a 0 HDX, like the second largest eigenvalue is actually 0. But maybe this is an uninteresting example. Let me try and give you another example. This might look ad hoc, but we will see very soon that it's actually not very ad hoc. Let's again look at our ambient vector space from before. Let me take x1 to be d-1 dimensional subspaces. Let me take x2 and x3 to be both copies, okay, so 2 copies of d+1 dimensional subspaces. And now I will connect edges according to the following rule. So if V is in x1 and S is either in x2 or in x3, then I connect V and S if V sits inside S. And if S is in x2, S prime is in x3, any guesses?
Intersection.
Intersection, right. So I connect S with S prime if the dimension of their intersection is D. Oh, Okay, I mean, there's kind of two separate rules here, right? I'm looking at this x1 to 3. Here I'm kind of using some containment, and here I'm kind of using this intersection derelation. But this already bears some resemblance to our code, right? Like the graph between x1 and x2, say, this is our graph which we use for the encoding, right? Like we took x1 to be v, x2, say, to be s. The graph between x2 and x3, so it's not exactly the decoding graph, right? Because we have two copies of every d plus one dimensional subspace, one here and one here. But we still have the same edge relation, right? So these graphs are very much related. Formally, the graph between these two is what's called the double cover of the decoding graph of the subspace code. But even if you don't know what the double cover is, you kind of see that this is, almost the same graph up to these like two copies. And one other thing that I may want to say on this example is that if, for example, I take S in x2 and I look at its neighborhood, then kind of just by definition, this will just be the local graph. Why is this? Really, it's just from the definition. If I look at S's here with this particular example, the vertices in here that will be connected are exactly the vertices inside S. The edges or the vertices in x3 that will be connected to S prime are all the S primes that intersect S on a d-dimensional subspace. And kind of the relation over here kind of by definition gives me this graph. There is nothing more to do here than just kind of stare at it. And so you should kind of believe me here that for every S, lambda of xs or gs is actually less or equal to 1 over, I'll write here 2 actually for safety, square root field size or something like that. And if you want to kind of prove sampling, you can also do this just using expansion. So
this is just for S in X2 or also X1?
Right, so this actually is true for S in X3 and S in X and V in X1 also.
Okay, but
so for this thing, of course, it's true also for S in X2 and X3.
Yeah.
For V's in X1, the link will look slightly different. We're actually not using the links in X1, but it will look slightly different, but still expanding.
Okay.
Okay, and
okay, maybe this is not quite relevant, but so your definition of two-dimensional high-dimension expander is to ask for like expander property on the neighborhood. So I imagine like for 3-dimension is like a nested definition, like
so a 3-dimensional thing will have 4 parts here, and every neighborhood will need to look like a 2-dimensional.
Okay, so it's nested.
You can that's one way to define it. Okay, so the code we're going to construct using the HDX that I will immediately tell you about is just going to take as the V side x1. It's going to take as the S side x2 union x3, and then kind of the decoding graph will just be the graph between the 2 parts x2 and x3, the x2 versus x3 graph, and all these local graphs are also going to be the links. So we're going to think about this example of the kind of baby code, which arises from this weird HDX that I described. And now we're going to kind of switch the HDX, but still use the same ideas. Okay, so this is going to be one side, this is going to be the other, and these are going to be the graph and the decoding graph and the local graph that I will consider. So finally, let me just define the HDX. I I'm sorry if this definition looks kind of arbitrary. It has some history carried around to it, and we'll just have to kind of take it as is. This definition needs a little bit of elementary group theory, which I also apologize, but we'll do it kind of slowly. So before I define X, I actually need a few objects. So I will denote by gamma.
Do you want to first do this or tell us how you use it? Like, tell us the parameters and how you use it.
No, I want to first define this. I think we need some time to kind of get used to this.
Just can you say what?
Yeah.
This thing is not good enough because
right. So this thing is right. So this thing is not good enough because the rate will be too low. If you look at the degree from x1 to x2 and x3, this is like 2 times the degree of the baby code, which the baby code itself, it wasn't good enough. And you can do the same thing like for the other type of degree. So really what we're trying to do is to take this kind of pattern and just to use it on a different HDX with a better degrees.
With smaller degrees.
Yes.
And what degrees you'll end up getting polylogarithmic degrees.
Right.
But that's one thing which I'm worried about. Your definition of high dimensional expander looks like something you could construct. So the random graph in some sense would satisfy this. And the usual high dimension expanders that I know are sort of very rigid objects that you can't generate randomly. So that's really equivalent to the standard high dimension.
Yes, I mean, you should think about it. I mean, we're kind of diverting here, and I really only have half an hour. And so maybe I'll just give a very short answer and you can ask me later. Like the problem with random objects here, if you want small degree, even, I don't know, logarithmic in the number of vertices here in each side, then your problem is that if you have a vertex V here, you sample its neighbors here, uniformly at random, unless like the degree here is like ridiculously high for like a birthday paradox or something, most of the time there will be no edges between these. So like not only it won't be an expander, it won't even be it will be trivial. And you can try different random models and kind of, I dare you to succeed. It would be very interesting if you had like a reasonable random model for this.
So in your like construction of S and V, you will use the expander property of vertices in V to guarantee the property too, like the short routing and the unique.
So I will actually like explicitly construct a routing function. I should say that kind of non-explicitly if you don't care about like the algorithmic aspects. Like existentially, there will just be a routing between these x2 and x3, just like by virtue of the fact that somehow like this also has to be an expander, which is maybe not trivial in an HDX, but it's true.
I see.
So it will have like low diameter, and you can kind of work a bit harder to also like make this almost unit congestion. But we want this to be like strongly explicit. Like we want to give an algorithm where you don't really need to look at the whole graph to find the routing. I don't know if this answered the question.
Yeah. So if you don't care about efficiency, then based on the definition of HDX and your construction, the property 1 and 2 will already be guaranteed.
I think so. I never kind of wrote this down entirely, but it should.
Okay.
It should be.
Okay.
I mean, you need to slightly work for this unit congestion thing, but with like good enough parameters for the HDX, you should have it.
Okay.
Right. Good. So so I was talking about this gamma. Gamma will be just a group of special linear matrices that are 3 by 3, so matrices with determinant 1, over some field extension fp to the k, K is going to be something like log n or something. This is just kind of to promise that I will have kind of enough points in my complex. The point will not be gamma, but pretty close. And fp to the k, I mean, it's a field extension, but maybe I should remind you that you can also think about this as concretely as a ring, where you're kind of looking at polynomials with this variable t. Now I'm thinking that t was my routing, but
Is a P the same P as before?
yes, it will be some prime which I need to set to be also polylogarithmic in log v and I.
Is there some R written over SL3 or? Like,
Sorry?
Is there some weird notation about?
No, this is me not erasing. Okay, so I'm thinking about just polynomials over this base field fp up to some like irreducible. And the reason I need this is that I will actually describe some subgroups, K1, K2, and K3. And these subgroups will kind of be subgroups that are supported on low degree polynomials in some sense. Let me just kind of define them. I think K3 is the nicest. Somehow, this is the names that stuck. So I'm thinking of the elements in the extension.
Zero is small, but
Yeah. Sure.
The case.
What? Oh, this wasn't
Entries
there.
of the matrix.
The matrix.
This is polynomials. I'm sorry that I'm using the same P, but you will understand from the X. So K3 will be upper triangular matrices where all these polynomials are low degree. Specifically, the degrees of P1 and P3 are at most 1, and the degree of P2, it's a quadratic, it's at most 2. So now you understand why I want to think about these specifically as polynomials. And K2 and K1, I mean, their definition is not very enlightening, but it will be just like the same thing, only the polynomials live in different coordinates. Let me actually just write K2 and K1. I will leave to your imagination. Right, so P1, P2, and P3, such as the same thing holds. P1 and P3 are linear, P2 is quadratic. Okay, and K1, like the only difference is that I kind of switch these two with these two. So maybe I won't write this down, but we'll need actually only K2 and K3 because we'll kind of, you'll see. Okay, so these are the two things. And our points in X, they won't be elements in gamma, they won't be elements in the subgroups, they will be cosets. So they will just be the cosets of Ki. So these are just translations of the subgroup with this element A. And I connect AKI with BKJ if the two cosets intersect. So if AKI and BKJ intersect non-emptily, and this is kind of equivalent of like taking as my edge set all things that look like AKI, AKJ, so two cosets translated in the same element, where I and J are distinct, and A is an element. Not that it's too important. So this is the definition of X. Okay, so I have kind of this, here's kind of a nice picture that I like. Here is gamma, here's like my whole group. And cosets of the group, they kind of define a partition. So maybe this is a partition of K1, here's like AK1, and so on. And K2, sorry for the different colors, K2 also defines a partition. Maybe I'll draw it in red. So maybe, here is K2, here's AK2, and so on. And this requirement, kind of pictorially, I see that K2, right, it should like connect with K1 because these two cosets intersect. So I don't know if this helps, but this is kind of what helps me parse this. So these complexes were introduced to the HDX community by Tali Kaufman and Nizar Oppenheim in 2018. In particular, here's their theorem. X is a 2 over square root p high dimensional expander where p is the base field size. Of course, for every field extension. Okay, so no matter what field extension you get, you still get this thing, which is nice. And I should also say, like, this was originally proved using like property T and all sorts of group theoretic machinery. A year later, Prahlad Harsha and Ramprasad Saftarishi, they gave a very elementary proof of this theorem, which I kind of recommend reading. I think it's really nice. We won't do anything with this theorem today, except for like stating it. And in particular, if I kind of use this paradigm on this HDX, because the neighborhoods would be these local graphs, as a corollary, these GSs will be samplers. If I take P to be large enough, which is like this polynomial in log V and the list size.
Some lower bound on K, but the extension.
Let's assume that K is like bigger than 5 or something, just so. Yeah, okay, like, I mean, these polynomials need to be quadratic, right? So like the degree should be at least 2, and I'm doing this for safety. But yeah, great. Great, and
When you're actually going to use it, you're going to take a big K or not?
so I am going to take a big K, right? So this is exactly the next thing I was going to do. Let's do some kind of elementary calculations here. For example, what is the size of x1? So this is just the number of cosets, which in a group, like the index rate, it's like the size of the whole group divided by the size of ki. So you can see that like in every k here, I have like 7 degrees of freedom, right? Like 2 polynomials of degree at most 1 and 1 of degree at most 2. So this is like p to the 7th. Gamma, maybe just believe me in this, it's like something like p to the, I think, 8k, something like that. And so kind of if you fix p to be some poly I and log whatever you want to get here, you kind of write it like this, then you can take this field extension to be even something that's kind of less than log x1, just because the base here of the log is large, and you will get like x1, which is kind of your target function.
It's circular.
Right, but let's ignore that.
In this case,
You know, I will say something. You write this paper with 4 authors, so everybody is like very pedantic at one specific thing, and I won't say who is pedantic about these things.
but we get it for every vertex size.
But there is somebody who was like very pedantic in this in the paper, and you can see that it's not circular. But you're right. Like in essence, this is also some kind of, it's like almost a power of p, and so you need to be slightly careful. Like you don't get this for all target values here, but like they're dense enough so that you can do some tricks. Let's not think about it. Like I didn't say anything about circuit complexity here, which is like a whole other category. Good. Where are we on time? Okay, good. So, one other thing that you should kind of suspect here is like, why would the degree here even be small, right? Like I want degree that's like polylogarithmic. And so here is a very nice description of neighborhoods in this graph. So here's my claim. AK2 is connected to BK3 if and only if there is some element, I will call it little h, inside K2, such that BK3 is actually the coset of AH K2. And okay, like one thing you can see here is an immediate bound on the degree. Because how many choices do I have for neighbors here? Like at most the number of the elements in K2. So this already gives me a bound of something like p to the 7 neighborhoods. And this is even before some double counting that's happening here. Like certain h's can give me the same neighbor. And this claim is really kind of just chasing the definitions. Because I mean, maybe it's kind of surprising at first. I don't know if it's kind of surprising, but kind of you see that, you know, AK2 intersects BK3, right? So they intersect on something, and that something must be an element, particularly of AK2.
You mean the coset of K3 equals the coset of K2?
No, sorry. Thank you. I'm like, seriously, this is like something that I really have, that if I don't get enough sleep, I can be easy on me. But you're right, thank you for it. Again, right, so what I want to say here is that if these two things intersect, in particular, the element in their intersection must be an element in K2. Right, so this means that there is something that looks like AH, where this H is in K2, but also sits in the K3, and once two elements sit in the same coset, they actually define the same coset. But I'm not just doing this claim to, I'm not just doing this claim for purposes of counting the number of neighbors, even though now you can see that if I take P to be like this thing, I still get something that's like polylogarithmic in x1 and in I, and this will give me like already like the rate and the locality that I want. Sorry, yeah?
So K should be at most like log over log, right?
Yeah. I wrote less or equal, but yeah.
Oh, okay.
You're right, like because the base is larger, then you can, I agree. In fact, for like very large values of I, it will even be like lower, and
okay.
You're not going to gain from this eventually, but that's like that's true kind of in the combinatorial level. In any case, why am I showing you this claim? Not just to count neighbors, but also this gives you a very nice way to route from two cosets. And here's kind of a nice way. Suppose I have some coset A, Ki, and some coset here B, Kj, and suppose I know how to write A inverse B as a product of matrices H1, H2, H3, up to Ht, where this H1 is in Ki, this H2 is in Kj, this H3 is in Ki, and so on and so on. Then I can immediately construct a path from this by taking AKI, going to, H1 is in Ki, so AH1 Kj, going to, well, A, H1, H2, Ki, and so on and so forth, up until I either reach Bkj or I reach Bki, and then I take one additional step to Bkj because they're both connected. Let's just say Bkj. So in other words, even if we ignore for a second like unit congestion and all that, if I just want to route in this graph, this kind of reduces to writing every matrix with determinant 1 as kind of this short product of elements in Ki and Kj, one after the other. So kind of really oh, I erased K2. You will have to believe me on what I'll say about K2 now. Okay, so kind of let's kind of say if we can decompose every, this is just a general element, but I'll write it like this, as some T length product in K2 and K3, then this will give me a T length routing scheme.
And you managed to do that?
Yeah.
Is it
That's
T or
a
K?
hard question.
Right, so this T, right, so this T, I mean, I wish it could be K. It will actually be something like K to the 2.3, unfortunately, for like,
What?
we will see.
What is that?
This is like log 5 of 2. I mean, log 5 of 2 is like 2.2 something, so
Okay.
I'm understating myself.
So what's the problem you solve? You get some two matrices.
Yeah, so I'm getting, okay, think of this as just some kind of A prime, right? I don't care anymore that it came from this.
You get some matrix in the group gamma.
Right. Now I need to write it as a very short product of,
Decompose it to.
yes.
Is it matter like you choose K2, K3 instead of like 1, 2 or like 1, 3?
Oh.
Are they symmetric? Like,
So it will be all the same, like.
okay, so they are all the same. Like it's not
I-
like in the previous example 1.
Yeah, so
They are
they're different subgroups. The proof will work for any like Ki and Kj. Specifically, we'll be using K2 and K3, which is why I'm like stating it for this. But that's
But you can also use it, like you can rename them and everything.
yeah, sure.
Okay.
Yeah, I can. Like if for some reason you need also, to route between like the V's and the S's, you can also you can also do it by the same manner, and we'll see like what the routing algorithm is, at least to some extent.
I mean, I guess I can imagine doing it when T is smaller than K, but when T is K larger than K, it seems harder to do.
No, T must be larger than K, otherwise you
Right.
can't build up degree.
Agreed, right? But
I'm not sure I understand the comment. Like, what do you mean?
in
You
this
can or
kind
you
of
can?
decomposition,
Yeah,
you gonna say something about it?
yeah, I'm going to do it.
Okay.
Like, why not? Okay, I mean, do I still have K3 at least? Yes, I do. Look, K3. These upper triangular matrices that have kind of many zeros, and we're not even going to use all of K3. We're only going to use matrices that have a specific form. These are elementary unipotent matrices. They look like this, E, I, J, R. They have ones on the diagonal. They have in the ith row and jth column, they have R and the rest are zeros. And these are like well-studied matrices. Also, a lot of them appear in like K3 and K2, which I erased. And kind of, we're not going to use all the building blocks in K2 and K3. We're just going to use these things that are in K2 and K3. So let me say a couple of things about these matrices. So first of all, ignore K2 and K3 for a second. If I have A prime, then I can decompose it to, I'll call them E1, E2, up to some constant. I think it's 36, where every EL here is some EIJ RL. And why is this? This is just Gaussian elimination. Okay? Like
These are IJ that are not, sorry, here I is less than J. Here.
In K3, I agree. Like in general, I'm just like let's just define this. Here, right I is less than J, and you can't put any R you want. You can only put low degree R's.
Right.
But here, when I'm doing this composition using Gaussian elimination, I'm actually using the fact that I'm over a field. You can do this over other rings, but let's just use fields. And I mean, these just correspond to row operations or column operations. So if you're looking at 3x3 matrices, this is true. So it's kind of enough to decompose each one of these separately, and I only have like 36 of them. So it doesn't hurt me because of the old notation. Here are a couple other things that we need to know about these matrices. First of all, these are, by the way, called Steinberg relations, or the sum of the Steinberg relations. If I product two of them, it's like taking the sum inside. So if I know how to construct an elementary matrix with R1 and R2, I don't know where this costs, I don't know, something, and this costs something, I can also do their sum again. And the other thing is that if I want to write the product, I write it R1, R2 like this, then I also have a relation that uses four matrices. This is like the commutator, so it's EIL R1, EL J R2, EIL minus R1, EL J minus R2. This is sometimes abbreviated using these square brackets. So EIL R1, EL J R2. Nobody's like clapping or something for me, like doing all the indices right.
And L is the third index.
Right, and here, thank you. Here I kind of need I, L, and J to be all distinct. So here, right, L is like the third index. And kind of just using these relations and the matrices inside K2 and K3, the elementary ones, we're going to construct every elementary matrix rather shortly by some kind of recursive algorithm. So, okay, yeah.
Just to clarify, so when R is like an arbitrarily high degree polynomial, right? So, okay, so
Right. This is true for any, this is true like on the level of algebra, like.
the decomposition of A into the 36 parts is like each part.
Yeah. These are not necessarily in K2 or K3. Like most of the time they won't be. Okay.
Do you really care about this value 2.6? If it was 47, you would be unhappy, or?
No, I don't. Like it could be. All I need is that this is a constant number. So if I know how to construct all of these, then I can just like concatenate. You know, they can even be like a logarithmic number, and then I will add something like here and this is just good so I can add some structure to my problem. Okay, and final thing, what EIJ are in K2 and K3. So here you'll have to believe me. So I have E12 PX, E13 PX, E23 PX, E31 PX, and E32 PX. I just want to note that like e to 1 is missing. And this is only for px's of degree at most 1. Now, before you jump, for some of these indices, I also have degree 2, but let's only take these. Like these will only be the blocks that we use. Okay, so to write any matrix like this, it costs me like one matrix inside either K2 or K3. Okay, I said that E to 1 is missing. How will we write E to 1 of Px if Px is of degree 1? Any idea? What? Right, exactly. Right, so if I want to write, oh no, E to 1 of, let's call it alpha t plus alpha x plus beta, I can just write it as the commutator of E to 3 of, I don't know, alpha x plus beta with E31 of the polynomial, which is 1. Right, so this matrix costs 4. Let's do a quadratic. Suppose I have I want E to 1 of like alpha x squared plus beta x plus gamma. Well, in this case, right, I can write it as like, let's do alpha x times x plus beta x plus gamma. Right? This is a product of two polynomials of degree 1. This is another polynomial of degree 1. So I can write this as the commutator of E to 1 alpha x, E to 3 alpha x, E31 x with E to 1 beta x plus gamma. Good. So this matrix costs 4. This matrix, right? I have actually a product of 5 matrices here. Every matrix here costs at most 4, right? So this costs me at most 5 times 4. This is a crude bound, right? Like most of these actually cost 1, but never mind. This is what we're going to do in general. And kind of right now I have some arbitrary polynomial here, which has, I don't know, like some degree 2m. I can always split it into the higher terms and the lower terms that have degree m. So if I have some polynomial px of degree 2m, I can always write it as x to the m p1 plus p2, where all of these have degree almost m, right? Just splitting the core, what?
Less than m.
Right, right, less than m. And then if I want to write e of px, whatever coordinates down here I have, I can just write it as the commutator of some other e of x to the m, e p1 times e p2. Right, and if this is ij, this would, here is il, lj, ij. So what do I get here? If maybe R is a bad letter because we already used that. If tau m is the maximal cost of some e p of degree at most m, what did we prove? We just proved that kind of R of 2m is less or equal to 5 times tau of m. Right, just from this. So kind of solving this recursion, you get that, you know, the maximal degree possible, tau of k, is at most 5 log k, which is roughly k to the 2.3, which is where this comes from. And you can imagine the recursive algorithm where you get a polynomial, you deconstruct these, you send these to the recursion, and so on. Let's not do it. And I see that I'm almost out of time. I won't prove that this is unit congestion. Maybe I would kind of just hand wave here and just say that the graph between x2 and x3 is like extremely symmetric. And the way that we proved, like the way we constructed this routing here, it seems like very specific, like I'm doing this deterministically even. But it turns out that kind of if you kind of symmetrize this routing by like also kind of randomly permuting back and forth using some like group elements, you can really like make this unit congestion. It's not a hard proof, but I don't have time, so I think this is kind of enough for today. So kind of let me just wrap up here. We constructed, this high-dimensional expander that, like, not only combinatorially it had like nice local spectral properties, but we also constructed like a very explicit or strongly explicit, in a formal sense, routing scheme here. And using this, we connected this to this combinatorial problem of like least recovery. I just want to say that I like this piece of math, and I think that like routing schemes should be used everywhere. Like another version of routing schemes with different properties was also used in this like very nice PCP construction by Wafna et al. And kind of, I think it's intriguing to understand better what you can do with these things if they're explicit, right? And like maybe just one kind of question to close. Existentially, I don't deserve this 2.3. Like I should just get K here, just by kind of considerations of expansion. And I'm not using any like sophisticated thing by like the field being large here. So like it bugs me that we're not getting the right, the correct constant here in the exponent, which should be 1. So.
But does it matter?
Okay, so for like least recovery and stuff, it turns out that if you can shorten the routing, you can take like better parameters, and you also get better query complexity, which I believe should also kind of match some kind of lower bound for direct product codes. Maybe. Other than that, it's not that I have something particular. It's just that kind of, that this thing, like this short routing exists, and like combinatorially, I think it's a very interesting question to find it.
So if you're okay with non-explicit routing, then you could get okay, right?
Yeah. In fact, in these graphs, because they're symmetric, it's even like very easy if you allow me like to run in polynomial time in like all of X and not polylogarithmic time.
Okay, thank you very much. Any questions? Other questions?
I guess one more question, this explicitness, is that just because you think the explicit thing is nice, or is there something in the statement of tolerability that really requires
Right, so we don't have here the definition, but really in this definition, these decoders are not just like abstract objects or functions, we really care about them being circuits. So like this routing, I essentially need to like embed it inside a circuit, so I really actually care about like the size of this circuit, and sometimes also the depth, like how can I parallelize this algorithm. And for that, I need this to be strongly explicit.
Okay.
And this is important for all these like complexity theoretic applications.
And also practically, right? Like I can build a code, say it takes only 2 queries.
Yeah.
But it takes me poly-n time to compute which 2 queries I need to make. Not very useful practically.
mathematician?
Yeah.
Sure.
You want it, time efficiency as well.
Yeah.
Like you should think about these graphs as like huge, like eventually you're going to use like these graphs where you have like some exponential size in the input that you're trying to compute. And so this is like, the right thing is to ask that these things be strongly explicit for this application.
All right. More questions? All right. Thanks again then.